thank you everyone for coming to our first LHRE lecture, Choi Chat, if you will. Today we're going to be doing it on the dot cam. Let me know if you guys would prefer whiteboard stuff, so we can use that for future lessons. But is everyone okay with this for today? Good. You guys, as general, do you guys prefer whiteboards or dot cams? No strong feelings?
I do not care at all.
Okay. Well, that's good to hear. So we're going to be dealing with statics. So,
Okay.
okay.
You have a red pen.
Do I have a red pen?
It will help with the contrast. It's fine.
Is it hard to see?
A little bit.
Do you want an orange pen?
I have a black pen.
Does that have black?
I have a red pen.
This is a pencil.
Do you want a red pen?
Yeah, the pen will help. You have a marker?
I mean, is it?
Sorry.
There's orange. It's patriotic.
Do you want?
That's the same. Now stick to the pencil. I lied to you. I'm so sorry.
Is that easier to see?
No.
I was gonna say, I don't think the pencil's that hard to see, is it?
That's true.
In the future, I'll try to use computer paper, but this is the only thing I had on hand. So unless someone has like computer stock paper. Anyways,
I do.
like actually?
Yeah.
Oh, well, do you mind if I take some?
Yeah. What do you do your computer stock paper? I just can use the print at my door for free. Alright, cool. Oh, I mean, you might need more.
This will probably be enough. Alright. We're good. We're gonna edit this out of the video. This is a do-over. Hi everyone. This is statics. We're here to learn about statics. So what is statics? Well, static means it means it doesn't move, right?
I think you can get it to stop autofocusing somehow, but I don't know how.
Yeah, probably. Oh, there we go. No more autofocus.
There we
Great.
go.
So we are dealing with statics. Statics is the physics of things that do not move. Some would say that's the physics of boring things. But to a bigger extent, and I think a more important takeaway from this, the thing you learn in statics is more so how to think about free body diagrams. And this is something that I think even people after they take statics, they don't really walk away with a good understanding of what a free body diagram actually is. I myself only really had it like click like that until I took like machine elements or something. I'm hoping I can get you guys ahead of the curve on that. Because I know you guys have all probably done physics 1, mechanics, you probably use free body diagrams a whole bunch, but there is like an essence that I wanted to kind of imbue onto you guys. And hopefully we can get a flavor of that today during this lecture. So, to start off, I want to kind of talk about what a free body diagram is. So we're going to be looking at free body diagrams. Or FBD for short. So a free body diagram is a diagram of a free body. What is a free body, you might ask? I'm sure you guys all know what a diagram is, so I won't go into that too much. But a free body, what is a free body? A free body is something that is unshackled from the universe, I guess you can think of. So let me kind of give an example. Let's say I have some sort of pendulum, right? It's just like a rope affixed to like a hook in the ceiling, and then it's attached to like some sort of ball, right? What we hope to do with a free body diagram is to kind of more precisely look at the forces any individual thing might be seeing, right? So this ball is going to have some sort of weight. It's going to pull down on it, right? This wall, this hook up here, is going to be pulling on it, pulling it back up, right? And when we look at the rope itself, if we try to like take this out of this system and we just have it alone here, right? And we want to model it in a way that will represent the actual universe it's in, we can, for example, and we're going to be going deeper into this, but I just kind of want to give you an introduction. We're going to be basically showing, hey, we can model this as just being pulled by some generic force, right? It doesn't have to be a wall, it doesn't have to be a ball. All the rod sees is a force pulling down and a force pulling up, right? So this is a free body, this rope here. We've taken it out of context and put in forces to model it the same way it would be in the real world. So another example, let's say I have some boxes, right, and they're stacked up on top of each other, right, and there's some sort of ground that it's sitting on, right, and I want to look at this box out of context. Well, I can take it out, and I know that it's going to be feeling some sort of weight coming from the top, some sort of weight coming from the bottom, or some force pushing it back up. And so this guy just feels like he's being squished, right? He feels like he's being squished. What are the forces exactly, and how do we know they're there? Well, we'll be going over that shortly. But basically, I want to get this idea of what a free body diagram is as a way to take a piece out of context, right? Now, for the most part, what I've shown you right here, it's taking out physical objects. But this sort of idea doesn't just pertain to a rope or a ball or a box. Let's say I want to look at some tiny part of this rope, and I want to take it out of context of the rest of the rope. You know? That itself too, right? Like imagine if I cut the rope in two, right? I can see that this tiny piece of rope will also feel forces pulling it up and pulling it down, right? It's not something that is solely done to objects. It can be done to parts of objects or multiple objects at the same time. It's as much as you want to represent. You can take as many things as you want and turn it into a free body diagram, right? But it's not restricted to the idea of just being a solid object that you're doing something to. It could be part of an object or multiple objects. So we're going to start out with a fairly simple example. We're going to start out by first looking at some simple static systems and try to figure out forces. We'll move on to moments and torques. And then I'm going to show you different boundary conditions and we'll get a feel for that. Okay? So let's start off with a fairly simple problem. I'm going to have a wall. This kind of dash mark means ground, like it's earth, right? It's something unmovable, right? Something rigid. I'm going to have a beam cantilevered from it, right? I'm going to assume it's a massless beam for now, for simplicity. And I'm going to say I'm pulling on it with a force F, okay? Actually, a force P. For some reason, loads are always P's. I don't know why, but they are, and you'll see it like that. So it's being pulled by some force P. And my question is, okay, what force is the bar feeling, right? There's going to, or I guess a more easy way to think about it, what force is the wall feeling, right? We know from Newton's third law that every force has an equal and opposite, every action has an equal and opposite reaction, right? Every force has an equal and opposite force attached to it, right? So you guys have probably seen this in Physics 1, so I'm not going to dwell too much on this, but basically, we know that if we take the wall out of context, it's also going to be feeling some sort of load P acting on it, right? This kind of makes intuitive sense to us, right? Because we know that if the bar is being pulled by P, we know the wall is also going to be pulled by P, right? And then I'm also going to do a free body diagram of the rod. This is going to be some P. This is going to be some P. How do we know it's P? Well, we know it's P because we took Physics 1 and we know about Newton's second law, which I'm sure you guys remember as F equals ma, right? They've been shoving that in your head since like the 6th grade or something, I'm sure. Third grade? Show off?
No. Third law.
Third law?
It's equal and opposite, man.
That's the third law. Second law is F equals ma.
Nothing's accelerating. I thought this was statics.
I know. That's why A is equal to 0. M0, which is equal to 0.
It's the third law. Cool.
Well, this is the second law. F equals ma, A is 0. It just so happens that in statics, A is 0. And I'm also going to make another modification. The summation of forces. So the sum of all forces is going to equal to ma, just so we can be a little more specific. So what does this mean? Well, let's look at the problem again, but without making any assumptions. We know that we're going to have some sort of wall, right? It has some sort of beam pulled by some force P. And we think there's going to be some reactionary force at the wall, right? So I'm going to model it as, let's take a free body diagram of the beam. We know that there's going to be some force P, and there's going to be some reactionary force. Let's say we don't know what it is, right? Let's say like we're an alien and we've never seen math or physics before, and somehow we've made it to Earth. And so some reaction force R, how do we know what R is? Well, if we take the summation of forces, we know, let's say we have a coordinate system where x is positive this way, all right? Then we know that P minus R is equal to 0. And so we do a little bit of algebra. P equals R. Nothing too crazy so far. I'm sure you've all seen something like this before. But I just want to reiterate and maybe recontextualize that so we can move on to weirder stuff. All right, cool. So we've done a simple force. We're going to look at a cantilever beam, but a lateral force applied now. So let's do the same thing. Force P. Okay. Now, we know at the wall there's going to be some reactionary force, right? Let's call it R again. We know it's probably going to be facing some way that way, so it can counteract the force P, right? What else does there have to be? We're going to be introducing something called a moment or a couple. You guys have probably seen it referred to as a torque. There's going to be some restoring rotational thingy, whatever you want to call it, also being applied at the wall, right? And maybe this will make more sense whenever I draw it out as a free body diagram. If I have a force P here, a force R here, if it was just those forces, this thing will start to spin. We know it's not spinning because it's a static problem and nothing's moving. So there must be some sort of restoring torque there. I'm going to be calling this a moment from now on. Torques are twisty forces, not bendy forces, and this is a bendy force. Does that kind of make sense to everyone? Torque would be like if I'm doing this. Moments are like when I'm bending it like that, right? That won't show up in the video, but whatever. All right.
You can stand right here. Do it.
Oh, no, thank you. So we'll call this M for moment. It's going to be some moment. So let's solve this again. We know that with Newton's law, sum of forces is equal to 0. Let's say it is y is positive this way, you know, just defining a coordinate system. That means P minus R is equal to 0. That means P is equal to R. You know, no surprise there. Now we're going to introduce something called Euler's law, similar to Newton's law. But this is saying the sum of moments is equal to I alpha. Don't worry what these are. This is, well, you probably have seen this in physics as well. This is acceleration, rotational acceleration, and this is your moment of inertia, mass moment of inertia. But alpha is equal to 0, so sum of moments is equal to 0. And so this is like a torque balance that you guys might have done in physics 1. We're going to call it Euler's law here. So there's a couple things we're going to do. You might remember, let's say this beam has a length of L, and you might remember from physics that this P term is going to create some sort of moment. In fact, it's going to be equal to P times L, and because Y is that way, if X is this way, that means Z is going into the thing. I'll talk about coordinate systems in a bit. I probably should have done that first. But we know that since Z in this right-handed coordinate system goes into the page, PL, if we take the right-hand rule, right, you have a force where you have a distance going this way and the force is going down, so your hand curls with the thumb going into the page. Into the page is positive. We have PL, and then this moment here, we're going to curl it like this, just like in the direction of the arrow. That's going to be negative minus m, and we know that m is going to equal to PL. So I went through a lot of stuff there. By show of hands, how many people are lost? So I know how much in depth I have to go.
That's good.
Okay, so here I just defined an arbitrary coordinate system. I tried to make sure it followed the right hand rule. If you don't remember, this is the right hand rule. We've got x, y, and z, or any combination of these three. And because I defined y as going downwards and x going up, z just so happened to be going positive into the page. Generally, z is positive out of the page, and normally you have a coordinate system where it's like x, y, and then z coming out. This time I did it a different way because this is how we kind of look at it when we're doing the car, and we're going to be doing examples related to the car. But yeah, how many of you guys have seen like torque balances before? Not everyone. Okay, so I'm going to spend a little more time going over this. The idea of a moment is basically how much twisty force you're seeing, right? It's like how much torque you're going to be seeing at one point. So formally, the definition of a moment, which maybe not the best way to explain it, but it's going to be some, it's a cross product of vectors, a distance vector, and a force vector. Basically what that means is they multiply like the right hand rule would suggest. I'm not going to go too deep into the actual theories of this stuff because I kind of want to spend more time on the practical aspects of how it affects the car. Mainly because we're trying to condense these lecture series to such a short amount of time. Like I'm trying to show you all of statics in 1 hour, which is, there's a lot in statics. I know we always joke about how you don't learn anything in statics, but there's actually a lot, you just forget it and never use it. But we're going to try to keep it as top level as possible. Is everyone kind of comfortable with this, or is someone not comfortable? Because it's not, I'll go through some more examples of how we can apply this. All right, to the people in the video, no one raised their hand, so if you're lost, I'm sorry. Just watch the last, like, 10 minutes or something.
You should have raised your hand earlier.
Yeah. Okay, so let's move on to some cool examples. We're going to apply this, and I'm going to talk about boundary conditions afterwards. Okay, so P, this is going to be a distance A, this is going to be a distance L. Okay, so I have a question for you guys. So these are pin joints, right? What a pin joint means is that it resists translational motion, but it does not resist rotational motion. In effect, it can resist forces and creates reactionary forces. It does not resist moments, and so it does not create reactionary moments. This guy is a sliding pin, which means he can only take forces up and down, not left and right. Does anyone know why I made these things two different things?
That's how bridges in real life work.
That's how what?
Bridges and beams in real life work. It's like when you put a force on the beam, it's going to bend, so it's going to make the beam shorter. So
Right,
it's gonna
so it's
move in.
basically, if we don't do that and we push down, we're going to introduce some side-to-side forces. But the fact that this is rolling, because if it bends, it's going to shorten in length, and that's going to cause some forces going this way. But here, we add little wheels so we don't run into that problem. Simplifies things a bit. Good, thank you. There's a whole bunch of these kinds of things. Like up here, we used a bunch of fixed beams, which means it resists forces and moments. These guys will only resist forces, not moments. So let's run through the calculations. With the description of the boundary conditions said before, does anyone want to say what kind of reactions we're going to be seeing here? What sort of reactionary forces or moments would we see? Basically, another way to ask the question, if I have the beam here and I'm making a free body diagram, I know I have a force P here. What are the other forces and moments resisting that force? Yes.
There should be an upward force on the right support.
Good. There's going to be some reaction here. Let's call that R1 for reaction 1. Anything else?
One on the left.
One on the left. Very good.
And also pointing horizontally on the left.
Pointing horizontally on the left. Okay. Pointing left or pointing right?
Doesn't matter.
Doesn't matter. Okay. Let's do it this way. Reaction 3. Okay. Any others? No? Very good. There are no moments. There are no reactionary moments because we're using pin joints. Thank you for listening. So, we have our free body diagram here. We did it on the beam, so now we can analyze the forces at the beams and the reactionary forces it's going to see. So let's start with the summation of forces in X. So that's going to be 0, and let's say X is positive to the right. And this is going to equal R3. And wouldn't you know it, there are no other horizontal forces, so R3 is equal to 0. So we can just like kind of ignore him now. There are no reactionary forces in X. Next, let's look at the forces in Y. And for fun, let's make Y positive upwards now. It doesn't matter so much. It just changes the signs of things. So we look here and we see we have equal to 0. This is equal to R1 plus R2 minus P. Very good. There's not much else we can do with this. I mean, we can move P to the other side, but we have two unknowns, right? And you might remember from algebra, if you have two unknowns, you need two equations, right? Or maybe you know that from linear algebra, both algebra. So we need another equation. So let's look at the summation of moments. And let's do it around this point. Let's call that point O or something. MO. We know this is also going to equal 0. So can anyone tell me what the reactionary, or what the moment induced by, or one of the moments? Someone list out one of the moments, and if it's positive or negative.
Negative from P to A.
Negative from P to A? All right, cool. And let's just double check. Yep. We check right hand rule. We know Z is going to be coming out of the board positive. So if we look at A across and then P is going down, that's going into the board, that means it's negative. So minus PA. What's the other one?
Plus RL.
Plus RL. Plus R1L. Very good. Plus R1L. Cool. So remember what we're trying to do here. We're trying to figure out what these reactionary forces are. If we look here, we have one equation, one unknown, and the moments. So that's great. Let's do some algebra. So PA is equal to R1L. We know that R1 is equal to A over L times P. Cool. Now we can plug this back into here. So we know that 0 is equal to, and we substitute R1 here. We have A over LP plus R2 minus P. And so if I put the P terms on the other side, we have R2 is equal to P, and it's going to be 1 minus A over L. I skipped a bit of algebra there. Everyone see that? Anyone confused about that? All right. So there we have it. We have one of them and the other one. Cool. Now, one important assumption we made is that the beam was massless. Generally, if you were working in the real world, you probably want to consider the mass of the beam. So why don't we try that? So we got P here. We know that the CG is right here. No, this is A. Know that this is L, and let's say the CG is at L over 2. And let's say that this beam, let's say it's made out of steel. Does anyone remember what the density of steel is? Because I don't. I think it's like, gosh, what was it? I want to say it was like 7,000 like kilograms per meter cubed or something like that. Does that sound right? 7,800 or something like that? Let's say it's some material where density is equal to 8,000. 8,050?
Yeah.
Oh man, I was close. Kilograms per meter cubed. Let's say this beam, right, has some width and height. Let's say this is equal to 10 centimeters. This is equal to what? 8 centimeters. Okay. Let's say it's 10 meters long, and let's say A is equal to 2 meters. Okay. Sound good? I think that's everything we need. Oh, and the force of gravity is 1g. Obviously. We're not on Mars or anything. Okay, cool. So, first thing we should do, let's draw a free body diagram of our beam. So we know we have a force P acting here. We know from before we have R1, R2. I'm going to ignore R3 because we already showed it's irrelevant. There's one more force though. Where would that be? Center of mass, very good. So we'll show him being pulled down by some weight total, okay? So let's start summing things together. So summation of forces in y, let's say y is positive upwards. We know this is equal to 0. It's equal to R1 plus R2 minus P minus weight total. That makes intuitive sense. The force that's going to be pushing up is equal to the force pushing down, basically. But again, we have two unknowns. Well, technically 3 because we haven't calculated weight total. Also, let's say this is equal to like 1 kilonewton or something. P is equal to 1 kilonewton. So, with this in mind, let's move on. Let's do this first. Let's calculate weight total. Who knows what weight total is going to look like? Well, we know that density. We know what the density is. So if we can find the volume, we can figure out what its mass is. And if we know its mass, we know that mass times 9.81 is going to be its weight. Okay. So weight total is going to be equal to density times volume times g, because this is mg, and we know that this is equal to rho times LHWG. And we know what all these values are, so let's just leave it at that for now. R1 and R2, on the other hand, we do have to do a summation of moments, so let's sum up those moments. Let's do it about this point again. Let's call it O. MO is equal to 0 is equal to, we have negative PA and plus R1L. What is the last one? There's one more moment. The weight. What's it going to be? What's that?
WL over 2.
WL over 2. Positive or negative?
Negative.
Negative. Negative T L over 2. Cool. And now we're trying to solve for R1. So let's move everything to the other side. So R1L is equal to PA plus weight total L over 2. Divide both sides by L. So R1 is equal to PA over L plus weight total over 2. Okay? We plug this back into here. We know that 0 is equal to, plug in R1, A over L, P plus 1/2 weight total, plus R2 minus P minus weight total. So we know that R2, we're going to move everything to the other side, is going to be equal to P1 minus A over L plus 1/2 weight total. I think I did that right. And let's figure out what these things actually are. So R1 is going to be equal to 1,000 newtons times 2 meters over 10 meters plus...
Minus 1/2 W.
No, so if we move this to this side, that's going to be plus weight total minus half weight total. Yeah, it's all good, all good. And 1/2 weight total, so this is 1/2 times rho, which is 8,000, times LHW, which is times 10 times 0.1 times 0.08 times G times 9.81. Does anyone have a calculator that cares to do that? This is like 200. This is plus like, this is 4,000, 4,000. This is like a tenth. This is like 10. So I'm gonna guess it's like around 4,200. How close am I?
3,339.2.
Okay. So R1 is equal to 3,539.2 newtons. R2 is equal to that, whatever that is. I'm not going to write that out because that's a lot more numbers than I thought. If anyone wants to calculate it for themselves, that'd be cool. All you have to do is like take this and subtract R1 and P, I guess. But yeah, cool. So this example is actually very similar to what you'd see in like introductory vehicle dynamics. So this is a very similar case to finding like the weight distribution of a car, which is kind of why I chose it. If we look real quick, so I'm going to show you like here's the thing we had before, right? This is the free body diagram from before, and if I have a car, it's a beautiful car. It has some sort of CG, right? It's going to have some sort of weight total, and it's going to have like reactionary forces here, right? If you look at that, that looks eerily similar to this, does it not? And so the answers we came up here are actually the same solutions to what we'd use to find the weight distribution of the car. So we know that R rear, or sorry, we call it weight rear, which is the weight on the rear wheels, is going to be equal to A over L weight total, and weight front is going to be equal to weight total times 1 minus A over L, where L is the wheelbase and A is the CG distance. Now that's pretty cool. And because of that, you'll see whenever you do dynamics, like vehicle dynamics, and if you're in the dynamic system, you've probably seen something like this in some form of another. They'll show up a whole bunch, like just knowing this is for rear, this is for front. Like that's a calculation that's done many a times. Um, so, with that, I would like to, so depending on how much time I had, I wanted to go over moments of inertia. I don't know if we're going to have time for that. Instead, what we might want to do is, I kind of want to, okay, so there is one thing that's kind of important, which is boundary conditions, which are very important, especially when you start doing FEA. A lot of times, even in industry, like a FEA or finite element analysis, it's basically like a simulation of the part undergoing forces. They have to redo those over and over and over again, sometimes because like they get the boundary conditions wrong. And it's actually a really important part of how this thing would behave. Because the forces and moments we get with these guys are very different from if we had it like this, right? Or even this, right? There's very different. They'll come up with completely different answers. And it's important that we recognize when we're supposed to use a certain boundary condition. So I've already gone through a couple, right? So for instance, we know that if you have a fixed, this is called fixed, and what that means is it reacts forces and moments in all directions. We have this guy, which is a pin, and this reacts all forces, no moments. We have a roller pin. This reacts vertical forces, no moments. And can anyone think of any other boundary conditions you might see in the real world? So pin is pretty easy to imagine. Maybe even roller is easy to imagine. Fixed, you know, you just weld something together. Are there any other boundary conditions you guys can think of? Yeah.
When you have live loads or dead loads.
What's that?
Actually, no.
Oh, sorry.
Or like bolts. You can
Bolts?
do bolts, yeah.
How would bolted joints? Yeah. How would you model a bolted joint?
When I did it in industry, I just did a rigid joint or like
A rigid beam?
joints.
Like a rigid bushing connection?
I tried that, but it messed up the meshing on FEA, so I did more of like a spring.
Yeah. So bolts are actually really complicated
Yeah.
to model. It's kind of ridiculous. Once you get into FEA, you'll realize that. And there isn't a very good. So bolted joints. This is basically. Who knows? And so so you can model them, and depending on how accurate you need to be, there's different ways you can do it. You can model it as a rigid beam connecting two surfaces. You can model it as a spring. You can model it as a stiffness bushing, right? Which is what I think you're talking about.
Well, I did springs with a really high constant for like.
Yeah. So that's like a stiffness bushing. Like you can apply stiffnesses to bushings.
Yeah.
There's this thing called a Huth bolt stiffness matrix, which is like even more complicated but gives you way more accurate results. Basically, for all practical purposes, if you're doing like hand calculations, it's generally okay to model this as a fixed joint. Because, you know, just by intuition, if I bolt two things together, I can't twist one of them, right? So as like a first degree approximation, you can imagine this as fixed, but when you're modeling them in real life, they have a stiffness to them and they get really complicated really fast. Any other boundary conditions you guys can think of? For instance, let's say I have a shelf and I pull out a shelf, I push in a shelf, it doesn't resist my forces. Like how would what are the conditions that like a roller like that would resist? So like, let's say, So
Oh,
I have a
sure.
little guide rail, and I have like 2 pins there. Like, what is that? What does that do?
Like shearing it?
Kinda. In terms of like this nomenclature though, like what's going on here? Yes.
It restricts the vertical movement and the moment.
Exactly. But it allows forces in one direction. So this is like a guided
Oh, roller fixed.
guided pin or guided slot, I would call it. And this reacts vertical and it reacts all moments. And so it's important that you kind of, and this is like different than a roller pin, right? And you can have roller pins, you know. So there's lots of different combinations you can do, and it's really important to be able to identify, you know, what joints you see in nature. And sometimes it's not so easy of an answer to give. Does anyone have any questions on anything we've talked about so far? Or is anyone lost or confused how to apply something? We went over some pretty simple examples here. If you guys want to do more complicated ones, we can, or I can show you some different material if you'd like. Do you guys have a preference?
New material.
New material? You guys want to do new material? Okay. So we're going to look at distributed loads. This would be a more accurate way to represent like a weight. So distributed loads. And I will get my notes out for this because there are some integrals we're going to be doing. How fun. You guys like integrals? You guys like calculus? Oh boy, let me tell you. Let's see. Okay, so what is a distributed load? Before I was showing you point loads, so I've shown like a load applied to a single point. But let's say we have right, and let's say we apply a load like this, where we're applying a load over the entire length of the part, and it's like a distributed load, right? This is inherently different. So like let's say it has some loading Q, where Q is some force per distance. Because we're just looking at this from like a one-dimensional standpoint, right? Obviously, you can expand this to a force over an area, which would be a pressure, right? But for now, we're just going to be looking at a force over a distance. And it doesn't have to be like that, right? It could have, for instance, we could have an example where it has some kooky distribution here where like, oh, there's a lot of force here, a little force here, who knows? Or, you know, it can be some discrete function, right? So imagine if it's like imagine if it's a sine function, right? And it actually goes positive in some areas and negative in others, right? You know, who knows? It could be any distributed load, right? Or, you know, it could be like a quadratic or a cubic function, you know, any random generalized distribution of force, okay? So a couple questions. One, what is the total force being applied? And two, can we model this in a way that's easy for calculations? Because if we had to deal all the math with this, it would be a pain. And so hopefully if you've taken calculus, you can feel the integrals coming. So let's start with the easier question, right? So like, let's say this is a distance L. It has a force distribution Q, some constant value. Let's in this equation, let's say Q is equal to some constant Q naught, right? Can anyone tell me what the total force pushing down on this beam is?
L Q naught?
LQ naught. Very good, because it's a rectangle, right? LQ naught. So F applied is equal to LQ naught, right? Because Q is defined as a force over a distance, and if Q is equal to Q naught, that means force times the distance will give us a force, right? A more rigorous way to do this, and in this case I will do like an actual derivation. I'm also going to maybe go a little over time because we started a little late. I know some of you guys are in powertrain, so I'll hold you like maybe a minute or two over, if that's okay.
Body two.
Body two? Well, let's look at some differential element, right, with length dx here, okay? Q is equal to some function of x, right? And so first of all, let's say, we did a summation of forces. This is going to be equal to, at all things x, at every length x, it's going to be q, like f of x times dx, right? So like if I look here, if I look at this differential segment, dx at some distance x, there's going to be some, this is going to generalize to a constant q value, right? Which has a value of f of x, right? And so the area of this rectangle is f of x times dx. Since we're doing that at every point along this line, we can say from 0 to L, f of x times dx. That's the total force, right? And I realize this might be some of your guys' first introduction as to how mechanical engineers do calculus and apply calculus to the real world. A lot of times it involves us like looking at a really small bit of the material, calling it some differential element, in this case dx, and doing math to that small thing with linear approximations, and it all works out in the end somehow. This is for what the forces are. That's all fine and dandy. Like we can look, if we go back here, f of x is equal to q naught. If we integrate q naught over dx, it's just going to be q naught L, right? But how about if we look at where the forces are, right? So here's the deal, right? This is equal to some force, right? Let's say we wanted to model, if we wanted to look at the force distribution acting on these two things, we might want to look at what sort of reactionary moments it'll apply. Like, if we look here, if this didn't have any supports, this thing would start spinning, right? Because we have force pushing down here, force pushing up here, right? So let's do a summation of moments and try to figure this out, right? Summation of moments is going to be equal to, since this is some distance x away from the original point, this is going to be x times f of x dx, because this is the force on this little guy, and we will integrate him again from 0 to L. Okay? And that will give us the moment at every point. And if we do that, this will spit out, what ends up happening is some, a moment in general is going to be a force times some distance, right? And so to make it easy on us, we can approximate it, or we can model it as this force applied at some distance d. And to find that value of d, we know that this is equal to some total moment, right? this guy here is equal to some total moment applied. If we divide this moment by this force, we'll get some d value. And so m over f is equal to d is equal to the integral from 0 to L x, f of x dx over integral 0 to L f of x dx. Everyone following? We drifted into some probably more uncharted territory for you guys. And this little d has a special name. We call him the centroid. He is the centroid of this thingamadoodle here. So some common centroids for a rectangle, the centroid is in the middle, right? Powertrain meeting, anybody?
Get out of
Just like, I'm going to stay for like the end of this thing and then come as soon as you can.
We'll be done in like a minute or two.
Okay.
Yeah. Thank you, Nikunj. So cool. Now you can kind of see how for any given distribution, some arbitrary distribution, we can figure out how the distributed load is going to force on our beam and where it will force. Okay? And we probably don't have time to do examples, but don't worry, this is usually not relevant unless it's like this case, right? Generally, you know, like if you have a mass, a distributed mass on, you know, like I have my own mass, I approximate a rectangular beam, right? So generally, I would only have to worry about this case, which is pretty simple. Doesn't generally require this calculus, but I thought it'd be cool to show you guys anyways. Are there any questions before we go? Okay, cool. On the next chat, we're going to be delving into probably more interesting territory. We're going to be doing solid mechanics, which is where we look at statically indeterminate situations, which you probably don't know what that means yet, but you will, don't worry. And it basically means we can do cool stuff like look at how much a beam actually compresses or deflects and things like that. So look forward to that. Goodbye.